Alright, so in the previous video we were trying to find the volume of this figure here. We came out with the idea that we're going to have some type of donut shaped cylinder with a hole in the middle, which we call a washer. And we were trying to figure out a formula here. And notice that we said that it was pi, the outer radius here was the outside part or the outmost part from the x-axis all the way to our function. So we said that the radius was given by the square root of x here. And then we're squaring it because again the area of the volume of a cylinder is pi r squared times h. So again we have pi and then we have our r here, so r squared, and remember that h is replaced with our dx according to what we labeled it there, what we labeled our cylinder right here. Then we went into the inside part of the radius, or the innermost part here in orange that you see. And I said that the radius is given by the distance from the x-axis to the most inner curve. Well, if you look at your inner curve, it changes, right? It all just depends where you are with respect to x. So for example, if you are, let's say, here, then whatever the function is evaluated here, that would be your height. But you could be way over here, and again, whatever the function is evaluated there would be your height. So that would be your radius. So your radius is given just by your function f of x. So we have x squared dx here. So again, this is the formula that we need to calculate the volume of this specific washer here. Now, this is just the volume for one washer. Imagine if I wanted you to find the volume for the whole thing, which is essentially the point of the problem. I mean, that's exactly what we're after. Well, you could think about doing this process over and over and over again. In other words, you can think about creating another washer right there, and maybe creating another one and another one. And I hope you get the idea that you would have to create infinitely many washers in order to capture the volume, in order to find the volume of this figure here that we've kind of sketched. So again, you would have to accumulate the volume of infinitely many washers in order to find the volume of the figure that we have here, the solid that we have here. So again, accumulating many or infinitely many things should ring a bell, and in your mind should pop up the volume, or I'm sorry, the integral function, right? So again, when you're accumulating many infinitely many things, you should be thinking about the integral. So we can say that our volume, our total volume, is going to equal the integral from a to b, and notice I still haven't said what my limits are yet. We'll figure that out in just a bit. From a to b, and again, here is my formula. This is my formula for one volume. This integral will go ahead and accumulate infinitely many volumes. So notice what I have in common though. I have a pi in common, so I'm going to factor that out. And then it looks like I have a dx in common as well. So what I can do is just write my dx towards the end. And on the inside, I'm gonna have this square root of x squared. So this square root of x squared minus, and now I'm going to have my x squared here. So this is the function that I need to find the antiderivative of and then evaluate from a to b. Well, let's figure out what our limits are. Notice that we're starting here at 0, and it looks like we are ending here at some intersection point. My picture has gotten so messy by now that I can't even make sense of it. But notice it looks like we're starting at 0, and we have some intersection here that I need to find. Well, to find the intersection, all you have to do, to find the intersection, all you have to do is just set the two equations, the two functions, equal to each other and solve. So think about getting rid of a square root. Well, I would just square both sides, so I would have something like this. And then I'd move the x over, so I'd have x squared minus x. Factor out an x here. Again, this is just good old algebra review. And notice that it's going to equal 0 when x equals 0, which is exactly what we have here, or when x is equal to 1. So it turns out that this intersection is 1. So we are going from 0, so this is going to be equal to the integral from 0 to 1. And we now have this formula here, pi, let's see, this x squared, I'm sorry, the square root of x squared is just really x minus x squared. And then we have our our dx at the end. Now, by now, hopefully you know how to evaluate this integral. We'll do this really quick. The antiderivative of x is simply just x squared over 2. The antiderivative of x squared is x cubed over 3. And again, we are going from 0 to 1. And again, if you use the fundamental theorem of calculus here, you will have, let's see, pi. We plug in a 1, we're going to have 1 squared is just 1 over 2, minus, if you plug in a 1 here, you'll have 1/3. So you'll have 1/3, 1/2 minus 1/3. And let's see, if I keep, or now I'm sorry, I got to plug in the 0. But notice if you plug in 0, you're just going to end up with 0 over 2, which is just 0, minus 0 over 3, which is also just 0.